Did you know a fascinating feature of the periodic table? It acts as a guide to trace the order in which electrons fill the subshells S, P, D and F. By understanding this pattern, we can write the electron configuration of any element. Hi everyone, this is Akhilanand Singh. In this small video, we learn the technique of determining the electronic configuration of elements using a periodic table. Let us check how closely the periodic table is linked to the electron configuration of elements. First of all, every element of a period in the periodic table has the same number of electron shells, and that number corresponds to the period number. The second similarity is the presence of SPDF blocks in the periodic table and the existence of SPDF subshells in the electronic configuration of elements. The S, P, D and F names are based on 100 years old historical spectroscopic terminology, where S stands for sharp, P for principal, D for diffused, and F stands for fundamental lines in the atomic spectra. The S block consists of elements of the groups 1 and 2, also including helium from group 18. All elements of this block have an electronic configuration where the last electron goes into a S subshell. Each S subshell holds at most 2 electrons, and the S block has two groups, group 1 and group 2. The P block consists of elements of the groups 13 to 18 excluding helium. All elements of this block have an electronic configuration where the last electron goes into a P subshell. The P block has 6 groups, and we know that a P subshell can hold a maximum of 6 electrons. The D block consists of elements of the groups 3 to 12. All these elements have an electron configuration where the last electron goes into a D subshell. Each row of the D block contains 10 groups, and we know that a D subshell holds maximum 10 electrons. The F block consists of elements called lanthanides and actinides. The electron configuration of all elements of F block is such that their last electron goes into a F subshell. Each row of the F block has 14 elements, and we know that a F subshell holds at most 14 electrons. In this section of the video, we learn to write the electronic configuration using the periodic table. First, take a periodic table and mark each period with subshells as shown on the screen. Mark all S and P block rows as 1s, 2s, 3s, 2p, 3p, etc. according to the period numbers. Start the first row of the D block as 3D and make the first row of the F block as 4f. Now you are ready to write the electronic configuration of any element. Example 1. Writing the electron configuration for chlorine. Step 1. Locate chlorine in the periodic table. It is in the period 3 group 17. We note down its atomic number, it is 17. Step 2. Start with the first element and trace through the periodic table until you reach chlorine's position. Begin with period 1. Fully traverse 1s subshell including hydrogen and helium. Record 1s2 as the initial part of the configuration, giving a full set of 2 electrons to the 1s subshell. Then fully traverse the period 2, which has 2 blocks S and P. Append 2s2 2p6 to the configuration, giving maximum electrons to both the subshells 2s and 2p. Now come to the period 3. This period has 2 blocks S and P. The S block has to be fully traversed, but we need to stop one position before completing the 3p subshell. Fill the 3s subshell with 2 electrons. Chlorine is in group 17, one position before the end of the P block, so we assign 5 electrons to 3p and append 3s2 3p5 to the configuration. Step 3. The overall configuration for chlorine becomes 1s2 2s2 2p6 3s2 3p5. Step 4. Verify the configuration by counting total electrons, which is 2 plus 2 plus 6 plus 2 plus 5, that is 17. It matches chlorine's atomic number, so the electron configuration is correct. Example 2. Writing the electron configuration for tin. We will use a shorthand notation for writing the electron configuration for tin. This notation uses the nearest noble gas with a lower atomic number to represent the core configuration, followed by the remaining part. Step 1. Locate tin in the periodic table and note down its atomic number as 50. Step 2. Krypton is the noble gas nearest to tin with the atomic number 36. We write its symbol Kr in square brackets as the core configuration. For the remaining part of the configuration, we traverse only through the last or valence period, that is period 5, until we reach tin. In this period, both the S and D blocks need to be fully traversed. We note down 5s2 4d10 as the configuration for these blocks. Tin is the second element in the P block, so our traversal must stop here. The configuration for P block is 5p2. Step 3. Putting the whole configuration together, we get krypton 5s2 4d10 5p2. Step 4. Verify the configuration by counting total electrons. For that, we sum up the atomic number of krypton with the electrons in the remaining part. It will be 36 plus 2 plus 10 plus 2, 50. That's equal to 10's atomic number. So the electron configuration is correct. Example 3. Writing the electron configuration for cesium. Step 1. Locate cesium in the periodic table. Its atomic number is 55. The nearest noble gas prior to cesium is xenon in the fifth period. Therefore, we begin the configuration with xenon and append to it the configuration for the valence electrons. After xenon, we need to stop at the first element in the subshell 6s. Thus, the electron configuration for cesium is xenon 6s1. Example 4. Writing the electron configuration for gold. For this example, we are going to use the elongated form of the periodic table. First, we locate gold in the periodic table and note down its atomic number, which is 79. The nearest noble gas prior to gold is xenon in the fifth period. Therefore, we begin the configuration with xenon and append to it the configuration for the valence electrons. All valence electrons of gold are in the period 6. After xenon, we cross the 6s subshell completely and our configuration up to this point becomes xenon 6s2. We need to cross 14 elements of lanthanides as well. Configuration after crossing the 4f subshell of lanthanides would be xenon 6s2 4f14. To reach gold, we need to continue in the subshell 5d and stop at its 9th element. Appending the configuration for the subshell 5d, the overall configuration of gold will be xenon 6s2 4f14 5d9. But there is a catch here. The d block elements have a tendency to steal electrons from the nearest s subshell and make the d subshell fully filled. They become more stable by doing this. Considering this behavior of the d subshell, the correct configuration for gold will be xenon 6s1 4f14 5d10. With this, we have reached the end of this video. Today we learnt how to write the electron configuration of elements using the periodic table. We discovered an unusual electron configuration for gold. Notably, many d block and f block elements exhibit similar strange configurations. We will discuss such configurations at length in some other video.